Scalable inside-out image-based rendering is a new system that lets you convert the rooms in your house into virtual computer graphics that you can navigate interactively. Now you can freely move around this photorealistic scene, and the reflections and highlights come and go accordingly. Everything in our reconstruction and subsequent image-based rendering pipeline is computed automatically once you capture footage of the scene. The user simply shoots in all directions using both a regular color camera and a standard color plus depth camera like the Microsoft Kinect. The system discards the frames that it doesn't need, so more is better during capture. To build a 3D wireframe mesh of a scene, we explored many existing algorithms designed to merge color images, depth images, or both. Ultimately, we adapted a standard structure for motion algorithm based on interest points to register the color images into a sparse 3D point cloud. The depth images are then fused onto that scaffolding. The payoff of this approach is that footage can be captured by non-experts and leads to reconstructions with coverage of the whole room. Such a global reconstruction is in agreement with all the footage, which is good, but we observed that some details, visible in just subsets of images, are then lost in this process. Looking through one of the color-only input images, we can see that object boundaries are near image edges, but not aligned precisely. For improved image-based rendering, we compute additional local geometry from just nearby views. While a local reconstruction may not agree with all the other footage of the scene, it does align more closely with details in a specific image. Now for the interactive rendering. Our image-based rendering is specially designed to cope with large scenes, while still providing good quality at interactive rates. Here, we show how increasing the number of input images affects quality and performance. Our basic method uses mesh simplification, enabling interactive frame rates with hundreds of images on a high-end PC. But considering all input views during rendering causes the frame time to be linear in the number of input images. For better scalability, we built a spatial tiling and prioritization process. This helps larger scenes run at interactive rates and makes the system usable on more modest hardware. The quality difference with and without tiling is minimal. To observe the qualitative differences in our rendering approach, we render the same scenes using several baseline systems. First, here, we see a non-IBR method where a single texture is computed and applied to the global geometry. Naturally, even places where the 3D reconstruction is very accurate are revealed as artificial when the virtual camera moves around because the single texture lacks view-dependent effects. Image-based rendering has proven itself superior in this regard. For example, Ortiz-Cayon et al. Have a state-of-the-art method that captures those view-dependent effects. However, it, and most other IBR algorithms, are designed for outside-looking inward scenarios, and it only uses the 4 input cameras that were closest to the virtual camera. Most of the missing regions would be filled in if more cameras were used, but the cost of rendering is linear in the number of images, and, for our test PC, only 25 input images could be accommodated by this baseline algorithm. With the same image limit, we also tried an unstructured lumograph rendering algorithm with a floating textures style fuzzy depth test. And we show our results. First, restricting ourselves to the same 25 input image cap for easier comparison. And then, using all 223 images ingested through our tiling algorithm. When reconstruction goes wrong, all algorithms suffer from noticeable artifacts, though our method is more robust thanks to our local geometry estimation step. Unstructured lumograph rendering is prone to revealing those same flaws in the global geometry. For example, the eroded hand on the doll or the deformed appearance of the lampshade. We proceed to show recorded results from interactively navigating through several scenes using our system. Our rendering quality is limited in a few ways. For example, when capturing this scene, the user did not shoot the books on the right in close-up, so naturally they look blurry. Also, insufficient coverage during capture could leave parts of a scene without relevant geometry. So, for our approach, good data capture is less about skill and more about thoroughness. Thank you for watching.